Number 7, conservation of energy. So what is conservation of energy? It means energy cannot be created or destroyed. That's probably what you've heard before. Okay? But there's another way to think about it. And the other way to think about it is the total energy an object has cannot change unless work is done. Right? So the total energy that you have can't change unless you do work on the object. If you don't do any work on the object, you cannot change its energy. The type of energy can change. It can turn from kinetic into potential, but the amount of energy cannot change. So what's the equation for conservation of energy? It is this. So the kinetic energy at A plus the potential energy at A equals the kinetic energy at B plus the potential energy at B. Now, you may be used to saying initial and final, and that's fine. You may be used to saying, sometimes you can say change in kinetic equals change in potential energy, negative change in potential. There's lots of ways to write it. The way I wrote it on the practice for y'all is this way. I think. Let me make sure that's actually what I wrote down. Yeah, here we go. Yeah, so this is the way I wrote it on the practice example. Okay? All right, so let's do an example here. So, conservation of energy example problem. A child with a mass of 13 kilograms climbs a ladder to the top of the slide. How fast will they be going when they reach the bottom of the slide, which is 0.4 meters above the ground? Assume they started from rest at the top of the slide. Okay, first things first. You must draw a diagram. And I'll make sure on the test to put that, but you have to draw a diagram for these. Okay? And the reason you have to draw a diagram is because there are some things I cannot know unless you draw them. And those two specific things are where is 0 and where are A and B. Because A and B are not necessarily always the beginning and the end. Sometimes they are, but that also will help me figure out the next part, which is the 0 point. So, first thing I need to do is draw a diagram. So I have a child. Tiny little child climbing a ladder. Totally looks like a ladder. To the top of a slide. And then they're going to go down the slide to the bottom of the slide. There we go. That looks ish like a slide. Actually, looks less like a slide now anyway. So, the first thing we need to do is draw the diagram. Then what we need to do is I need to know at minimum where are A and B, and I need to know where is the height 0. So A is going to be the first part of it. So it talks about the child climbing the ladder to the top of the slide. How fast will they be going when they reach the bottom, which is 0.4 meters above the ground? So the kid starts on the ground, climbs to the top of the ladder, goes from the top of the ladder to the bottom. So we have to decide where are A and B. Now, it's pretty obvious to me where B is. B is at the bottom here. And the reason that's obvious to me is because it wants to know how fast are they going at the bottom. So I need to have that be my ending point, is B. But do I want A to be at the bottom of the ladder or A to be at the top? Well, at the bottom of the ladder, no work has been done, so there's no energy. When the kid climbs the ladder, they do work to give them energy, So at the top, they'll have energy, and that energy will turn into a different form of energy at B. So I'm going to call the top of the ladder A. So I need to know where A is, I need to know where B is, and then here's the next big decision you have to make. I need to know where is 0. Now there are 3 most likely places to put 0, and it's a choose your own adventure. You can put it wherever you want, okay? You can make the ground 0, you can make A 0, or you can make B 0. It does not matter which one. Heck, you can make anything 0. You can be like, oh, Mr. B, I'm going to call 0 4 meters above the ground. I don't know why you do that, but you can absolutely do that, okay? It does not matter what you call 0. I am going to show you an example where I make the ground 0, and then I'll tell you what you would need to adjust if you made A or B 0, okay? So all you have to do is just draw where your 0 is. I'm going to make a line here at the bottom, and I'm going to write H equals 0. That way I know where 0 is. It's at the bottom. Okay, once I've got that figured out, now I'm ready to solve for what's going on. So knowns and unknowns, and the rest of all that. So I have a mass of 13 kilograms. I climb a height of 3 meters, so that means my height at A is 3 meters above the ground. That's convenient. I made the ground 0, so the height at A is 3 meters. Okay, how fast will they be going when they reach the bottom, which is 0.4 meters above the ground, okay? So B is 0.4 above the ground. That's also convenient because I called the ground 0. So HB equals 0 meters. Okay, so now the next step is to figure out the types of energy we have at A and the types of energy we have at B. And the only types of energy we have are potential and kinetic. So the equation for potential energy is mgh. So the mass at A is 13, because it's always 13. G is 9.8, because it's always 9.8. And the height at A is 3. So when I do that, 13 times 9.8 times 3, 382.2 joules. Okay, same thing for the potential at B, M, G, H. .96. Okay, now I need to find the kinetic at A and the kinetic at B. So the kinetic energy is 1/2 mv squared. So I do 1/2 times the mass, which is 13, times the velocity squared. Now I need to know what the velocity at A is. I didn't mark that down yet. So now let's go back to the problem and see, what's the kid doing at A? Okay, climb the ladder to the top of the slide. How fast are they going at the bottom? Assume they started at rest. Okay, so VA is 0. So 0. Well, 0 squared is 0 times 13 is 0 times 1/2 is 0, so KE at A is 0. That's convenient. KE at B, 1/2 m v squared. Now I need to figure out what's the velocity at B. Okay, how fast will they be going? Okay, so I'm solving for the velocity at B. So I just write VB squared here. So the kinetic energy at B is 1/2 of 13 is 6.5 times VB squared. So now I'm ready to plug in and solve this equation here. So KE at A is 0. KE at A is 0. Here, let's Let's break these up so I don't get them confused. K at A is 0, plus the PE at A, 382.2, equals the KE at B, which is 6.5 VB squared, plus the PE at B, which is 50.96. And now it's all over but the shouting. So all we got to do is get the numbers by themselves. So I'm going to subtract 50.96 to the other side. Okay, so when I do that, I get 331.24 equals 6.5 VB squared. Divide both sides by 6.5. Let's stick to my sign convention. Gives me 50.96. That's VB squared. I don't want VB squared. I want just VB, so square root both sides. And the answer is 7.14 meters per second. By the way, it's only a coincidence that this number, when I divided out the 6.5, was equal to this number. It's a coincidence. It's just the numbers I picked did that. It's not an actual pattern. Human brain likes to put patterns with things, but there's no pattern there. Okay? Questions? Excellente. Okay. Here's what I want y'all to do. Go to practice 2.